हाँ हेलो हेलो सर, प्रेजेंटर बना दिया आपको। हाँ यार, प्रेजेंटर। हाँ
Hello, hello. My voice is audible, sir. Chittakan, sir. Hello.
हेलो सर, हाँ ऑडिबल है, ऑडिबल।
Okay, sir. Okay, good afternoon all. Then today we have the last session, last talk on this online workshop on emerging CMOS technologies and beyond trends and challenges. Today, the discussion of topic is your statistical simulation and RF analog performance of FinFETs. So already the many research, many experts, they already pointed out the advantage of these emerging devices, why this emerging device came out into the picture or in the semiconductor industry. And they have already discussed those things because to overcome the short channel effect or to follow the Moore's law, we have to go for the advanced MOS devices. And like your tunnel FET, FinFET or junctionless, so among the FinFETs also one of the most emerging devices. See, today statistical simulation means today point of discussion is what we discussed means already it is pointed out that the high K or metal gate is used as the gate material, or that means the metal gate is used as the material instead of the gate polysilicon, because the polysilicon has some depletion effect problem. In order to overcome those problems, the metal is used as the gate material. But when you use the metal as a gate material, it has some, it will produce some random work function in the gate area, and which in turn affects the electrical properties of the device. Okay. Today we will discuss this one. So we have discussed this one by performing the statistical simulation, and also we discuss the FinFET structures. Mainly we discuss the dual material FinFET structures, RF analog performance. Okay. So these are presentations, the evolution of MOSFETs, Moore's law, ITRS, a view on the technology note, then scaling, means expert talk. Although I will give the brief overview on this one. Then I will discuss the FinFET and simulation of FinFET structures. I have included one analytical modeling also in the FinFET structure. Then conclusions. Okay. So evolution of MOSFET. In 1947 from the Bell Laboratory, William, then John and Walter, they have dated this BJT, but later on what is observed that the BJT, due to the saturation problem, due to the surface precipitation problem, the BJT got saturated. In order to overcome those problems, again Atala and Kang from Bell Laboratory in the year 1956 invented a new device and named it as a insulated gate field effect transistor, which is popularly nowadays known as MOSFET. Okay, as you know, this is the one structural view of the MOSFET, schematic of the N-type MOSFET. So the MOSFET, I think you know, the MOSFET can be enhancement mode as well as the depletion mode. In the depletion mode, what happened already, there will be channel will be there in the source and the drain. But in the enhancement mode, what will happen? You have to apply the gate bias in order to create the channel between source and the drain, so that the electrons can flow from source to the drain. As a result, the current will be flow in the device. But it can be like your N-type as well as the P-type also. Whatever the structure is shown in the figure 1, this is N-type MOSFET. So in this case, in the N-type, both the source and the drain are highly doped. That means degenerate and plus semiconductor, and your body is your P-type semiconductor. And this is an enhancement mode device. What happened? It is already discussed also previously that when you apply the small gate voltage, then there will be depletion region will be there. But applying the larger than the smaller gate voltage, inversion region created. Like this, there will be inversion, moderate inversion, or the strong inversion. And as a result, the current will be flow when you apply the sufficient amount of gate voltage. The electrons will flow from source to the drain. And as you know, the electrons flow means what? Q equal to IT. That means the current will be flow from source to the drain. You will get current in MOSFET. And insulated gate field transistor, that means this is the MOSFET structure on. Okay. So like this, Moore's law. Gordon Moore, who is the co-founder of the Intel, in the year of 1956, he predicted that what the number of transistors per square in integrated circuit roughly double by every 2 years. Double by every 2 years. See, this is the published in Electronics in the year of 1965, and as you can see, this is your corresponding the plot of your number of components per versus your year. And as you can see from this plot, what you can observe, when the number of components is means in this region, the number in the power of 10 to the 3, in the year of 1970, your per integrated circuit, and this is what related cost. That means the cost is also less, the number of components also more. Like this, you can be in the year 1970. Okay, that means what in the small area, because of the reduction in the device dimension, you can fabricate more number of devices. Morse revised his prediction, and because of and he announced that the number of density on an electronic chip would be doubled by every 18 months instead of your 24 months. Okay, see the figure 3 shows the, as you can see, ITRS insulator or your FinFET structures. It got means in the 2010. It came into picture in the year 2010. Similarly, semiconductor also. Okay, see, this is the prediction up to till 2020. This figure shows the prediction up to 2020. Like this, another point is your ITRS. ITRS means International Technology Roadmap for Semiconductor. See, which is popularly nowadays known as IRDS, International Roadmap for Devices and Systems. See, it has what is the function of ITRS? It has motivation. Actually, it identifies the essential requirement. Means, for suppose the current technology node 10 nanometer or 7 nanometer technology node, in that technology node, what are the various requirements of your on current, off current, or threshold voltage, etc. The various electrical property, it will identify that requirement. It will be notified by the ITRS. Similarly, it points out the solution to the problem and the limitation in the present time. That means what are the limitations in the present semiconductor industry, or it points out those problems, and it also try to find out the solution or to overcome those barriers. Okay. Then ITRS also finds out the area where no solution manufacturing exists and invites the academy or the industry to do the research in those areas. That means what it will means where no means in order to find out the solution to a particular problem or to overcome the barrier of your MOS devices, it invites the industry and the academics to do the research in that area. Okay. See, this figure shows the feature size as a function of time. As you can see, the feature size of the device reduces as the time increases. Okay, like the gate time also reduces as the time increases. See, next is your view in the technology node. This is already this point in the by Dr. Chittakan Sahu. See, the technology node, as you can see, technology node means what? There is a reduction 90 nanometer to 65, 45, or what 32, then 22. So this reduction in the technology node means that the technology node means is your gate length. So the technology node means what? Half of the pitch. What is the definition of pitch? Pitch means that in a IC or in any silicon chip, there is a two metal contact. These two metal contacts are there. Okay, these two metal lines are there. Between two metal lines is called your pitch, and half of this pitch is called your technology node. Okay, the definition of the technology node means what? Half of the pitch is called your technology node. See, like this, in the year of 2003, technology node is 90 nanometer, 2005, 65 nanometer. Similarly, 2011 is a 22 nanometer. See, according to Moore's law, what you have to do, you have to reduce the your device dimension Okay, suppose you have to reduce, this is on device, okay, and you have to reduce, you have to make it half. Then that means that you have to reduce half by 1 by root 2. Is it or not? You have to both reduce length and width by 1 by root 2. See, this technology node also defined according to like this. If you multiply 90 into 1 by technology node. Similar 1 by root 2 means what? Again 0.707, 0.707. Then you will get the next technology node will be your 22 nanometer. Like this, you will get technology node or 16 nanometer technology node. Okay. See, again, you can see these are the various research area. See, in the 65 nanometer technology node, the gate length is 30 nanometer. These dimensions are defined by ITRS. Similarly, 45, 20, 20 nanometer. 22 nanometer technology node means what? The gate length is 10 nanometer. Like this, as you can see, this is a tri-gate operation structure, or the in the 2011, that means tri-gate operation is what? Your FinFET structure. Okay. Then this is your, like this, there is some research area in the 2015 to 19. Good 3-5 semiconductor or argon nanotube. These are the various prominent research area. And see the technology node definition already is the half of the pitch is called your technology node. See the advantage of scaling, as we know, to improve to follow the Moore's law, of course, you have to do the scaling of the devices. But in terms of speed also, similarly, the package density also improves, because what will happen if the device dimension reduces within the same area, you can accommodate more number of means chip or device. That is the package density of the with the scaling, the package density improves. Similarly, what your speed also improves, because suppose you reduce the length, that means the on kind of the devices improves. If the on kind of the device improves means what? The delay, in terms of delay also, delay will be less. Average delay will be less of the device. That means the device will be more faster. Similarly, the cost also reduces, and the as well the static power consumption also reduces with the scaling of the devices. But the scaling, it has some limitation also. See, these points already pointed out by previous speakers. So the scaling, it has some, as you told, as when you do the scaling, various short channel effects will occur. Various short channel effects will occur means what? When you do the scaling of the length, then source drain, there will be some depletion region at the source drain, between source channel and between your drain channel. Okay, like you decrease this channel length, then what will happen? There will be some depletion region between this source channel, come very close to each other. If this depletion regions will come very close to each other, and like this, there will be some leakage current also with the scaling of the devices. Like if you do the oxide scaling, then gate leakage current will be low. See, that means what? This should not be happening in any particular devices. That means we have to overcome those things. Okay. That means the scaling leads to the various structural effect, like your high, your timing is very lowering or leakage current. Similarly, subthreshold swing also degrade with the scaling of the devices. Okay. But in the conventional MOSFET, the subthreshold swing is limited to what? 60 millivolt per decade. We cannot reduce the subthreshold swing below 60 millivolt per. At temperature equal to 300 Kelvin, you will get the subthreshold swing per. Since off current with the scaling, off current also increases. Off current of the devices also increases with the scaling of the your MOS devices. That means if the off current of the devices increases, that means we cannot apply those conventional MOSFET for application. Your current should be very low, leakage current should be very low. But if we do the scaling, the leakage current also increases. That means which should not be happen. That means we cannot apply the conventional MOS device for low power application. See this for this technology node, like for 45 nanometer technology node, the supply voltage is 1 volt, like this for your 1 micrometer technology node, it is 1.3 volt. Next, then what to maintain the speed and to maintain the power density without we have to reduce the device along with the power along with the threshold voltage of the integrated circuit, and to reduce the off current and power delay product. See the gate can be, it should not affect the current, unlike the conventional devices. In the conventional devices, what we observe in the MOSFET, with the scaling of the gate length, the current of the device, that means leakage current, increases, which should not be happen in the in the advanced devices. Then another point, as we discussed, the subthreshold swing in the MOSFET is limited to 60 millivolt per decade, but it can be over tunnel. See the tunnel FET already discussed yesterday class, that yesterday lecture, that tunnel FET operation, it provides the subthreshold swing below less than 60 millivolt per decade, and the operation of the tunnel FET also depends upon the thermionic emission. Sorry, band-to-band tunneling operation instead of your thermionic emission in the MOSFET. Okay, so due to the low of current, the leakage current energy, leakage energy can be reduced and improve the energy efficiency. And emerging device also to reduce the short channel effect. So emerging device, it will provide also the low of current, so that you can say the energy efficiency also improves in terms of leakage current. And the advanced devices also reduce the short channel effects. So next, then why the FinFET transistor? Okay, so already to follow the Moore's law, we have to increase the number of transistor, as we already discussed, and which leads to what downscaling of the device dimension. But it results in various short channel effects. Okay, see the researchers have proposed the various structure to overcome these short channel effects or to follow the Moore's law. The FinFET also one of the favorable devices because it can control the gate, because it controls the channel from all over the gate. Okay, because it has more gate control compared to the your conventional MOSFET. And Chen Minghu and his group in the year of 1998 first coined this term FinFET because the structure looks like a fin. That's why they term this the fin structure as FinFET. Okay. The figure 5 shows the difference between your double gate and the single gate structure. Like double gate means FinFET and single gate means is a conventional MOSFET. As you can see from the structure, here red color indicates the single gate and the blue color indicates the double gate. As you can see in the left hand side, drain-induced barrier lowering, and in the right hand side, it is a subthreshold swing. Both the parameter DIP and the subthreshold swings are less in case of double gate compared to the single gate. Also, with the length of the scaling also, it is always less compared to your single gate. Both the value of DIBL and the subthreshold swing. That means what we can say in terms of short channel effect, due to having the more gate control, the double gate performance is better compared to the single gate devices. That means compared to your MOSFET, the FinFET performance is better. Okay. So next we'll discuss your structural difference between FinFET and your conventional MOSFET. First, we have to know the structure of the FinFET, how it looks. See, like your conventional MOSFET, this is a conventional MOSFET. The figure 6A represents MOSFET and figure 6B represents the FinFET. As you can see, the MOSFET is what? The channel is horizontal. Channel is horizontal, but FinFET, the channel is vertical. This is a fin. This part is a fin. The channel is vertical. Okay. See, the conducting channel is horizontal, and in this case, your fin is wrapped by oxide. All over your fin, oxides are placed and this will act as your gate dielectric material. And this gate material are placed at right angle to this what fin, okay, and it wraps over whole the fin. See, as you can see, this is a one gate, this is another gate. That means this is a double gate FinFET. And in this case, what will happen? This is the structure of fin. This is a normal silicon body. It will here some source will be there, and here drain will be there, and in between this, the channel will be there under this oxide and the gate material. Okay. In case of FinFET, the total fin width is given by 2 into height of the fin plus TSI. TSI means what? This thickness of the fin is called your TSI. Thickness of fin is called your TSI. The width of the fin is given by 2 into height of the fin, your TSI. Okay. This height plus this height plus your TSI is the total width of the FinFET. And this is a normal conventional MOSFET. Okay. See, the working principle of FinFET similar to MOSFET. That means it also works on the principle of thermionic emission. Like the working principle is what? The working principle of your FinFET is similar to your MOSFET. When you have applied a small gate voltage, a depletion region will be created. And when you apply what? A positive at high positive gate voltage, the semiconductor surface will be inverted from P type to the N type. As a result, the charge current will be flow from source to the drain, and there will be flow of the current. But similarly, you have to apply of course the drain to source bias voltage. The current will be flow between source and the drain. Like your MOSFET, working principle of the FinFET is similar to MOSFET. So next we'll discuss the types of FinFET. Okay. See the FinFET, first we'll discuss the double gate FinFET as well as the triple gate FinFET. So one thing also you note down, the FinFET can be both the N type as well as the P type. Like your MOSFET, for N type, both the source and the drain will be N type material, and so your channel will be P type. Like in your P type, source and drain will be P type material, and channel will be what? Your N type material. Okay. See, this is the structural difference between double gate FinFET and triple gate FinFET. The FinFET, it can act as both double gate as well as the FinFET as well as the triple gate FinFET, depending upon this oxide thickness. See, as you can observe from this figure 7a, the oxide thickness of this top gate is larger compared to this front gate. If you consider this is front gate and this is back gate, compared to the oxide thickness of the front gate and the back gate, top gate oxide thickness is very large. As we know, the oxide capacitance is given by epsilon by Tox. Okay. See, if this oxide thickness is very large, that means what? Gate capacitance, gate control over the channel reduces. That means what? In this case, it will act as your double gate. Okay. That means only this gate 1 and gate 2 will have the impact on the electrostatic potential of this FinFET, and as a result, it will act as a double gate FinFET. Similarly, as you can see from this figure 7b, this thickness is comparable to your front gate and the back gate. Both the front gate, your gate dielectric, and the back gate dielectric, as well as the top gate dielectrics are almost same. Means they are equal. Okay, that means all the gates have the same impact on the channel. And as a result, it will act as what? Triple gate. That means in this case, the top gate also will have the influence on the electrostatic potential of the FinFET structure. And this is the structural difference between a double gate and the triple gate FinFET. That means depending upon this oxide thickness, it will act as a double gate FinFET as well as the triple gate FinFET. Similarly, this is the structural difference here, shorted gate and the isolated gate FinFET. Okay. HG means in this HG means shorted gate and IG means isolated gate FinFET. See, a shorted gate means what? This is of course this is a double gate FinFET. In shorted gate means what? It will what? Both the gate 1 and the gate 2, they are shorted. As you can see, the gate 1 okay. That means it is shorted gate FinFET. But in the figure 8b, gate 1 and the gate 2, they are isolated. This is your on gate dielectric material. In this case, as you can observe, the gate 1 and the gate 2 are isolated from each other. That means what? The gate 1 and the gate 2 will act independently in the circuit. And this type of structure is called an isolated gate FinFET. Okay. Similarly, the figure 9a and the 9b is your symmetric gate and the asymmetric gate FinFET. See, in this case, depending upon the work function value, it may happen that you are applying the same work function to both the gate 1 and the gate 2. Also, you can apply the defined work function to the gate 1 and the. If you apply the same work function, to both gate 1 and the gate 2, like this is your gate 1 and this is your gate 2, then it will act as what? Symmetric gate FinFET. Like in this case, in figure 9a, gate work functions are equal for gate 1 and gate 2, and it will act as a symmetric gate FinFET. Similarly, the work function may be different. This structure you can see that there is a difference in the color also in the gate 1 and the gate 2 in the asymmetric gate figure 9b. In this case, it indicates that work function value are defined for both gate 1 and the gate 2. Okay. That means what? In this case, it will act as a what? Asymmetric gate FinFET. Okay, work functions are different. So these are the structural difference between your FinFET. And this is an interesting fact on the FinFET, as we already informed that Chen Ming-Hu, who is the TSMC distinguished professor in University of California, invented this FinFET structure, and he's the father of FinFET. And in the 2020, I got the IEEE medal. And when he sketched this FinFET structure, when he's fly to Japan, and FinFET is the result of a sponsored project, a project by DARPA. DARPA means Defense Advanced Research Project Agency of US government. Okay, this Chen Ming-Hu's first job was tutor for high school. Later on, he became assistant professor at MIT. Okay, now he is the professor at University of California, Berkeley. Next, we'll discuss a few simulations in the FinFET structure. Okay, as I have gone through the literature parts I have not included. I have included only the whatever I did in my research. Okay, as I have gone through the literature, what happened? We have observed that if you reduce the whole, then there is reduction in the both on current and the off current. Okay. See, in order to overcome this one, we have proposed a new structure. This pin looks like a step. As you can see, this pin looks like a step. Okay, and name this FinFET as step FinFET. And we have observed that there is significant amount of reduction in the off current, but on current is not reduces by that much of significant amount compared to the conventional FinFET. In this case, figure 3a represents the what? Your step FinFET, a 3D structure, and this is a 2D structure of step FinFET. And this is what? This is a conventional FinFET 2D structure. Okay, it has two different oxide thickness and thin width. Like this is a silicon. Similarly, we have considered two different material. Germany also we have considered. Okay, and see, before doing the simulation, we did the calibration of the ticket model. Okay, see, whatever the dimension we have considered as per your 10 nanometer technology node. The dimensions we have considered for this structure as 10 nanometer technology. Okay, see, this is the calibration of the ticket model. We did the ticket model calibration in terms of both input as well as the output characteristics. See, what is the purpose of calibration? Actually, what happened? We did our work in the ticket simulator, but simulator it takes the by default whatever the by default results or default models are there. It will take automatically that one. In that to get the realistic result, that means we can at that time it may happen that our results whatever we are getting that may not be realistic because there is no experimental validation. And to get the realistic result, what we did, we have taken the experimental data from the literature. We have taken the experimental data from the literature. Then we have adjusted the various parameters in the ticket simulator, like mobility parameter or your then doping dependence mobility parameter. Then we have adjusted also work function of the gate material also in order to match the experimental result with the your simulator. Okay, and it is observed that the both the your transfer as well as the output characteristics shows the better matching with the your experimental data. Here symbol represents the your what experimental and line represents the your what simulation. And it's better matching or better agreement is observed between experimental data and the simulated data. See next, and whatever the physics models we have now, the experimentally calibrated physics model that we have used for rest of the simulation, so that we can say our result is validated up to certain extent. Next is the comparative study of the step FinFET in terms of we have taken the, as I told, ITRS requirement. And this is the your comparative. This red color is a step FinFET in terms of transfer characteristics, and this black color represents the conventional. C FinFET means conventional FinFET, and this is your linear scale. This is your log scale, and as you can see, there is significant improvement in the off current for the step FinFET due to having the better gate control. But on can also reduces, but not that much of significant amount. And as you can see, the on-to-off ratio we got in the order of 10^10. Similarly, subthreshold swing also we got 67.54 millivolt per decade, and drain interest barrier lowering we got 42.05 millivolt per decade. Whereas in case of conventional FinFET, the current ratio or the switching ratio we got in the order of 10^5. SS we got 74.18 millivolt per decade, and the DIB we got 54.71 millivolt per volt. Okay. See, that means our step FinFET shows the better electrical characteristics compared to the conventional FinFET. See, next we have also the horizontal electric field. See, the horizontal always the gate should be controlled by channel should be controlled by vertical field. That means the vertical field should control the channel. But when we have also observed that in terms of horizontal electric field, if the horizontal electric field is more, that means what? The hot carrier effect also will be more in the MOS devices. And it is observed that the horizontal electric field is less in case of step FinFET compared to the conventional FinFET. And that means what you can say, the device will be better in terms of hot carrier effect, the step device compared to the conventional devices. Similarly, as you can see, the gate capacitance also less in case of your step FinFET compared to your conventional FinFET. That means in terms of the step device will be more faster compared to the conventional devices. Okay, because capacitance more means what? The delay also will be more in case of your conventional FinFET. And also we have plotted the impact ionization rate. And as you can see, the impact ionization rate also more in case of your conventional FinFET compared to the step FinFET at the drain channel junction. At the drain channel junction, it is more compared to the conventional FinFET. See, next our topic of study is what? Statistical simulation. Okay, so what is in that respect, actually what happened? As already told that nowadays we are using the metal as the gate material. But when you use the metal as the gate material, when you do the deposition of your metal, the growth of the metal cannot be uniform. It may happen that there will be some growth is not uniform, that means it will be non-uniform. And as a result, it has various orientation, and it has various work function value in different orientation. Okay, and that means what? At that time, your metal gate cannot have a single work function value. Always what we did in the aluminium, or if you have any other gate material, gate polysilicon, we have used a single work function value. But due to the deposition technique, or due to the metal growth, non-uniform metal growth, the work function value cannot be uniform throughout the gate. And in order, when it is not uniform, it has various work function in defined orientation. And due to having the defined work function value, it has the impact on your threshold voltage. That means ultimately it will affect our what? Electrical characteristics of the devices. Okay. See, in order to study this one, we have considered titanium as the gate material, and we have used one random algorithm in order to study the work function. See, WIP means what? Work function variability on electrical parameters is measured. Okay, we have used the titanium as the gate material, and we have used random algorithm in the simulator to study the effect of work function variability in the state FinFET structure. Also, we have considered, we know that the metal, it has some grain, okay, there will be some grain, and we have considered non-uniform grain with average grain size. Okay, we have considered various grain size, okay, and each combination of the structure we have simulated 200 times to find out the variation in electrical parameters like threshold voltage, on current, or sub-threshold swing, etc. Okay, see, these are your work function value, and what is the probability of getting this value we have considered from the experimental paper. And in the orientation 200, the work function value is 4.6 for titanium metal gate. Similarly, in the orientation of 111, the work function value is 4.4 electron volt with probability 40%. We have considered this value in your simulator, ticket simulator. See, as you can see, this is the top view of the randomization of the work function within the gate area. This is the randomization of the work function from ranging from 4.4 to the 4.6. And the figure 2 shows that the line represents what your 200 samples, and symbol represents the nominal value. Here you can see this is the corresponding transfer characteristics, and this is only the means. And this is the corresponding value, and here 200 data are there. 200 IDUG characteristics are there. Here sigma VT represents what? Variation in the threshold voltage, and phi bar means this is your grain size. Like this, we have the grain size 15, 10, 7, 5, 2 nanometer. 5 combinations we have considered, and this is the number of area by G represents the grain size, area by G square. Okay, that means what? If your width of the length increases, the number of grain increases. So the sigma means what? The variation in the threshold voltage. That means, as we know, the statistical n increases, the sigma reduces. As you can see, the variation in the threshold voltage reduces as the channel length of the devices increases. Because if the channel length increases, what? The n increases. If n increases, then the variation in the threshold voltage reduces. Okay. Similarly, the width increases, the variation in the threshold voltage reduces because the n increases. However, for various grain size we have observed. Similarly, if the grain increases, then what will happen? N reduces. If n reduces, if grain size increases, n reduces, that means what? Variation in the threshold voltage increases. However, as you can see, when the grain size is 15 nanometer, it got almost constant. Because in that case, the number of grain within the gate area is very less. It may be happen only 1 or 2. Because the length is your suppose 16, 12 nanometer, and it is the length size is almost equal to your grain size. That's what the threshold voltage got saturated with irrespective of the gate length for grain size of 15 nanometer. And similarly, we have observed the on-kind variation also. Similar off-kind variation also. The on-kind variation also reduces as the channel length increases. Similarly, off-kind variation also reduces. And like with increasing the grain size, the variation in the grain can also increases. Okay. And we have for better visualization or better explaining the results plotted that we have done distribution we have plot the distribution plot of the threshold voltage, on current, and the off current. As you can see, for small grain size, that is close to normal. Larger grain size, it is your binomial distribution. Okay, for like your grain size 10 nanometer at the 15 nanometer. Similarly, as you can see, when you go from this grain size 2 to the 10 nanometer or the 15 nanometer, the variation in the threshold voltage is increases. Like for on current also increases. Similarly, the variation in the off current also increases when you there will be this span, this the variation the off also increases. Like, but one thing you observe that the this by this span and this one is not greater than your 0.2. The difference between these two is not your greater than 0.2 because the titanium metal gate has the work function difference of 0.2 only. Okay, like this. See, this one in the transactions on. We have done the another analysis. We have now did your comparative study between conventional and the silicon step devices, and in terms of the dielectric constant. Okay, what we did, we have considered only for two gate size 7 and 5 nanometer. When we have observed that as the dielectric constant of the gate material increases, the variation in the threshold voltage also increases. But due to having the better gate control, the step device shows the less variation in the threshold voltage compared to the your conventional devices. Why this happens? Because with increasing in the your dielectric constant, what happened? The potential also increases. That's what your variation in the threshold voltage also increases. Similarly, the as K increases, the variation in the subthreshold swing. Okay, the subthreshold swing reduces because as dielectric constant of the gate dielectric increases, the gate control over the channel improves, which leads to the less variation in the threshold, less variation in the subthreshold swing. Okay, this of course your variation in the electrical properties will degrade. Similarly, the step shows better subthreshold swing performance in terms of variability compared to the your conventional devices. And the histogram plot for this your what threshold voltage and the subthreshold swing comparison. Here, this one represents a conventional the silicon step device material is SiO2. As you can see, the variation in the threshold voltage is less in case of step device compared to the conventional devices. Okay. Similarly, when you are using the lanthanum oxide as the gate dielectric, then the variation in threshold is SiO2. This is the SS variation. The SS variation is more in case of conventional compared to the step device. Okay, but using the high the variation in the threshold, variation in the subthreshold swing can be reduced. Okay. What we did, we have used some other channel material. Other channel material means we have considered germanium as the channel material instead of the silicon. Okay. We have observed the result whether how it behaves with the various channel material. In the germanium step device we have considered, and as you can see, the germanium device, it shows the less variation in the threshold voltage compared to the silicon up to this range. Okay, but from here it got saturated. That means when your gate length is comparable to what your grain size, the variation in the threshold voltage is material independent. That means whatever the may be the material, the number of grain is constant, or the grain size is comparable to the your channel length of the devices, then the variation in the threshold voltage is almost constant, whether it may be silicon material or germanium material. See, in order to examine this result, we have see why it happens, because the germanium, it has higher dielectric constant. Due to having the higher dielectric constant, it shows better performance in terms of variability compared to the silicon. See, in order to examine this result, again, we have plotted the potential plot. As you can see, divide the channel in the three defined section of three different work function. Near the source and the drain work function value is 4.5, and the in between that the work function value is 4.4 electron volt. And as you can see, the variation in the potential from your higher the low work function value is here more in case of your silicon device compared to the germanium. In case of silicon, it is 33 millivolt. In case of germanium, it is here 8 millivolt. More variation in the due to having more difference in case of silicon, it shows the germanium value is 8 millivolt. Okay. So next we have the Pilgrim's plot. This is the name of the scientist. Plot means what? The plot between your variation in the threshold voltage versus 1 by square root of effective area. As you can see, the threshold voltage is less for germanium device compared to the silicon. Red color indicates the germanium compared to the silicon. Similarly, as your under 1 by square root of effective area increases, the variation in the threshold voltage increases the increasing the number of drains within the gate area. Okay. See, this is up to your whatever we discussed, that is up to your statistical simulation due to in presence of metal gate work function variability of in presence of work function variability of the metal. Okay. So like this, next we'll discuss the next topic of interest or is what comparative analysis of SMG, DMG, TMG, FinFET in terms of RF analog and linearity performance. See, SMG means what? SMG means simply your single material gate device. That means okay, SMG. And DMG means what? Dual material gate FinFET. Okay. And TMG means what? Triple material gate FinFET. See, the structure DMG and the TMG FinFETs is already there, already in the literature, but analog performance comparisons are not yet reported. That's what we have done this analysis. So what is the advantage of this type of structure of DMG and the TMG? First, I'll discuss that one. See what happened, as we know, the figure 24 represents the your dual material gate FinFET, DMG FinFET, and figure 24b represents the triple material gate FinFET, that means TMG FinFET. In this case, two different materials are considered, metal 1 and metal 2. In this case, we have considered three different gate material. Okay. The work function value also we have given. Metal length, thin with thin height, oxide thickness, okay, and source drain, and this is a barrier oxide box. This is a SY FinFET, dual material gate, and the triple material gate FinFET. So what happened in this case? See, we have considered the work function value of this double material gate. In the FinFET, the work function value of metal 1 is greater than your metal 2. Similarly, your also this is a triple material gate. Is there any questions? Okay, doubt sections we will discuss later. Okay. See, this is a metal 1. The metal work function of phi M1 is greater than phi M2. And one thing you note down that always the minimum potential point, and it is near your source, In case of what happened, in case of what? In case of this dual material, there will be some depletion region between this metal 1 and the metal 2. Similarly, here also there will be depletion. So then metal 2, metal 3. Then normally what will happen? There will be shift in the minimum potential. This is your potential in case of conventional FinFET. But in dual material gate, if you increase the drain bias, the minimum potential will not change. Between this metal and the metal 2, there will be some depletion region. When you increase the drain bias, it will in between this metal 1 and the metal 2. That means what? It will not impact. It does not has that much of impact at this channel junction. As a result, there will be no means the threshold voltage roll up will not be there in case of your what dual material gate. That means it will has the better short channel characteristics. Like this, in case of your triple gate also, in case of triple material gate also, the minimum potential will not change and we will get the better electrical characteristics. But our interest is the dual material and the triple material gate. See that these are the various dimensions that we have considered for the triple material and for the your FinFET. So this is the comparison of the horizontal electric field. As you can see, the horizontal electric field is less for both dual and the triple material gate compared to the single material gate means conventional FinFET. And due to having the lower horizontal electric field, you can say it will have the better short channel effect or the less hot carrier effect compared to your single material gate FinFET structure. And this is the we have considered 4.77 electron volt, 5 and we have considered 4.1 electron volt. Similarly, for triple, these are the work function value is 4.77 electron volt. Then the transconductance, it plays the very important role, and it is used to find out the gain of any circuit. Okay, and the transconductance relation, the derivative of the drain current with respect to the gate voltage at fixed drain bias. As you can see, both the dual and the triple material gate FinFET shows the maximum transconductance compared to the single material gate FinFET. Okay, but at high gate voltage, at a high gate voltage mobility or due to the degradation in mobility of the carrier, there is degradation in the transconductance also. Okay. Another your analog performance parameter GM by ID. Already the definition is already discussed in the yesterday class. Okay, by when this is what is the importance of GM by ID or VIP2, VIP3, those things. This is actually your transconductance generation factor. As you can see, the TGF also improves with respect to your TMG and the TMG devices compared to your single material gate devices. That means what? In terms of your analog performance, the DMG and the TMG are also better compared to conventional devices. Okay. See, next we have the cutoff frequency, but inside this gate capacitance also. Okay. As you can see, the gate capacitance also increases with respect to your DMG and the TMG FinFET, but the variation in the improvement in the transconductance is more compared to the changes in your capacitance, and which leads to the improvement in definition of cutoff frequency is the frequency at which short circuit gain is 1. As you can see, the cutoff frequency for the both DMG and the TMG FinFET compared to the single material gate device. That means in terms of RF performance, it shows better performance compared to the single material gate devices. And TFP means what? Transconductance and frequency product also. Transconductance and the frequency performance in material gate devices. Okay. That means what we can say, the transconductance and frequency means what? It will measure the both analog as well as the RF performance of the devices, and what we can summarize that the RF and the analog performance is better for SMG, for DMG and the TMG FinFET compared to the single material gate devices. See, next, this is your VIP3 and VIP3 means what? Voltage intercept point, where first and the third order harmonics are same. And this is a IP3 plot. As you can see, the peak value of both the VIP3 and the IP3 are more. That means what? See, what is the importance of linearity? Linearity means what? If any system is linear, means what? There should be no distortion. That means we can use this device for any communication system. Okay, so that there is no noise or there is no distortion. Okay, so in the linearity performance only in terms of VIP3 and the IIP3 because it has the more impact compared. There is other parameters also VIP2 or your IIP2 like that, but we have not compared that one. We have directly compared the VIP3 and the IIP3 because see the VIP2 it can be balanced in the it can be adjusted in the circuit by using some balanced modulator circuit. Okay, and as you can see, it is more for your SMG and TMG and DMG devices. Similarly, IIP3 is also more. That means in terms of linearity also, this DMG and the TMG device provides better performance compared to the SMG devices. Okay. See, this is up to what? This is your comparative study of your comparative study in your what I said SMG, DMG, and the TMG FinFET structures. See, next topic are effect of the temperature on your RF analog and the linearity parameters in DMG FinFET. See, as you know, the temperature also plays a very important role. So, whatever comparative study in terms of your DMG, SMG, and TMG FinFET, that we did in a fixed temperature 300 degree Kelvin. Okay, but it may happen that temperature is changing from this location to the suppose we go to the Jammu, there will be some different temperature. In Jaipur, there will be some different temperature. But that means we have to measure the performance in terms of temperature also. That whether device satisfy the whether the device has the capability or not to provide this much of voltage, this much of current, voltage, or transconductance, whatever. Okay. In order to analyze that one, we have studied the RF analog performance. The RF analog performance of the DMG FinFET. So as you can see, this is your first we plotted the transfer characteristics in the linear as well as the log scale. As the temperature increases, both the on current as well as the off current of the devices degrade. Okay, both the on current as well as the off current of the device degrade, and as you can see, the off current also increases, decreases. But when temperature increases, the energy band gap it has major impact at the lower gate. The energy band gap reduces using the off current of the devices. Similarly, at higher gate bias, the mobility of the devices reduces. There will be temperature. Okay, that's why the on current also temperature increases. The transconductance, like transconductance also shows the similar pattern like your what I said. Transconductance also reduces as the temperature increases, and there will be degradation due to degradation in the mobility at high gate bias. The transconductance, there will be roll up in the transconductance. Okay. Similarly, the gate capacitance it has major impact in the higher gate bias. Because at the lower gate bias, the energy band gap reduces. That's what will happen due to the degradation in the energy band gap. There will be the electrons can easily electrons can easily cross the barrier between source and the channel, and they will come to the channel. There will be more channel in the charge. Okay, in order to balance the charge, the gate charge also increases. Gate capacity also, the temperature increases. This is your RF performance. The cutoff frequency reduces as the temperature of the devices increases. Similarly, the gain transconductance frequency product. See, gain transconductance frequency product, it measures the overall performance of the device. The GTFP means gain transconductance frequency product, measures the overall performance of the device. As the temperature increases, the overall RF analog performance of the device also degrade. That means we can summarize that as temperature increases, the RF analog performance of the DMG device degrade. So next we have to study the linearity performance. See that this for that purpose we have first to plotted the GM2 and the GM3. So GM2 means what? GM2 represents the derivative of the drain current. double derivative of the drain current with respect to gate voltage. Similarly, GM3 means what? Triple derivative of gate current with respect to the gate voltage. Okay. As you can see, the higher the value of this parameter, then what will happen? The distortion. Higher the value of this parameter, that means what? There will be more distortion in the circuit. Or if you apply this device for any communication application, then there will be some distortion if the value of GM2 and GM3 are high, because they represent the higher order harmonic in the circuit. Okay. As you can see, as temperature increases, both the GM2 and the GM3 reduces. That means with the increasing temperature, which is expecting that below the linearity performance of the device improves. That means as temperature increases, the linearity performance of the device will be improved. Okay, whereas RF analog performance are degraded. In that respect, we have plotted the VIP2 and VIP3. VIP2 and the VIP3, better will be the linearity performance. VIP2 means what? Voltage intercept point where first and second order harmonics are equal. Similarly, VIP3 means what? Voltage intercept point where first and third order harmonics are equal. As you can see, as temperature increases, both the VIP2 and the VIP3 are improves. That means what you can say, the linearity performance also better. Okay. See, next we have plotted your IIP3 input intercept power, where first and third order harmonic powers are equal. Okay, and this is your INT3 means what? Intermodulation distortion. Intermodulation distortion. See, IIP3 value should be large, so you can say the linearity performance is better. But INT3, that means distortion, should be less. Okay, so on this plot IIP3, the value of what your IIP3 are more as temperature increases. That means it helps us better, it gives a better linearity performance. Similarly, the INT3, the distortion parameter or amount of distortion reduces as temperature increases. That means what we can say, as temperature increases, the linearity performance of the device improves, whereas your RF analog performance of the device degrade in terms of your DMG device. Okay. So up to this is your whatever I discussed. That is your RF analog performance of the DMG, TMG, and TMG, SMG, FinFET. Also, we have discussed the effect of temperature in the dual material gate FinFET. Okay. See, next topic is your the analytical modeling. The analytical modeling in DMG FinFET. Okay. So only we discuss the surface potential modeling and the subthreshold swing and the threshold voltage modeling. Okay. See, the DMG structure that already we have discussed is your figure 35A, represents the 3D view of the DMG FinFET, and figure 35B represents your 2D structure of the DMG FinFET. So in order to perform your modeling of this DMG structure, what we did, we divide DMG into, we divide this DMG into two parts. One is the asymmetric gate, another one is a symmetric gate. Okay, and we apply the parameter weighted method to find out the surface potential modeling. See what we did, why it is asymmetric and why it is symmetric. So in this case, what happened? Both the gates are present. You see both this gate and this gate are present, and oxide sections also are equal, and it is also present. That's why this is your symmetric gate. Means we divide this symmetric gate, and this is asymmetric gate because only one gate is present. Okay, and this is a buried oxide that we have considered. See, the importance of analytical modeling is what? After doing the analytical modeling, what we can do? We can apply this to your circuit. For the circuit simulation, always we need the analytical modeling. Okay. See, we have to find out the surface potential modeling. We divide this one to the asymmetric and the symmetric gate FinFET. Okay. See, these are the various assumptions that we have considered while doing the modeling. See, the monomobile charge carrier are considered in the model. Similarly, we have not considered the interface step, like in between the your SiO2 or the channel, that means between gate oxide and the channel, there may be some interface charge. We have not considered that charge. Similarly, there are no immobile charge carrier in the gate dielectric. We have not considered any gate leakage current in this while doing the modeling. Then we have not pointed, or we have not taken under consideration the source channel, channel and depletion region, any kind of your mobile charges. The surface potential at the source and the drain are constant by giving the expression related to the Fermi potential of the two regions. Okay. Then next, this is the, I briefly tell the derivation of the modeling of surface potential in DMG FinFET. Okay. See, this is the normal for Poisson's equation. So you have to solve the Poisson's equation. Okay, for asymmetric gate, DMG FinFET can be determined by this Poisson's equation. See, these are the various boundary conditions that we have applied. Okay, we have considered electrostatic potential between there is some boundary condition. However, is the boundary condition between this source channel, between this drain channel, between this metal, like this, between this oxide and the box, like this, there is some boundary condition that we have applied. Okay, as you can see, y equal to 0, you can apply the simple continuity equation epsilon 1 E1. This condition we have applied epsilon 2 E2. Okay. According to the fin height or fin width, similarly we have considered the potentials are equal between metal 1 and the metal 2. Like this, see, this is the surface potential at your source site, okay, at which will be a built-in potential only. Similarly, built-in potential plus your bias between your drain to source. Okay, this is your surface potential at the drain side, and this is the surface potential at the source side. After solving that one, we got the potential. Whatever we have taken the potential in this vertical direction, we have considered. This is your parabolic equation. Okay, then applying the appropriate boundary condition, we solve this one, and we got this is your asymmetric potential under metal 1, and this is asymmetric potential under metal 2. Similarly, we have not written here the coefficient A1, B1, and this thing. Similarly, the under symmetric condition, by applying the same technique, we can find out the potential under your symmetric case, or under metal 1 and the metal 2. Then what we did, we have applied the parameter weighted method to find out the potential of the DMG FinFET under M1 and the M2. Okay, and this is the phi 1 and the phi 2. Where P12 and P13 represents the P12 means what? TSI by TSI plus 2 of the height of the fin. And P13 means what? See, this is in terms of width of the fin. P13 is in terms of width of the fin. And P13 is in terms of height of the fin. Okay, P13 is equal to what? 2 into height of the fin by TSI plus 2 into height of the fin. Okay, so this is the surface potential under M1 and the M2. Similarly, we can find out the minimum potential. How to take the derivative of the surface potential in the equation for 15 and the 16. We will get the minimum potential as this one, and for symmetrics and the asymmetric case, and this is the total minimum potential for your DMG FinFET. And subthreshold swing, by taking the derivative, by applying this equation, we can derive the subthreshold swing formula where Nm is equal to given by this one. Okay, and after taking the derivative, we will get the subthreshold swing formula. And as you can see, this Nm is a function of what? Minimum surface potential. Next is the threshold voltage. To find in multi-gate device, the threshold voltage is defined as voltage where minimum charge density carrier Q inversion becomes equal to your QTH. See, the Q inversion charge formula is this one. We have applied this one, and we have taken the minimum potential. We replace this under this exponential term. We have put the minimum potential value. See the QTH. How we got the QTH value? So this is your threshold charge. This threshold charge we have find out from your simulator. So for that purpose, we have done the multiple simulation, and what we did, we find out the value of the minimum charge, and we have take the average value, and we got the minimum charge. After taking the average, we got the threshold charge is equal to 3.72 into 10^11 coulomb per centimeter square. Then we have equate this one to this inversion charge, and we got the threshold voltage formula will be like this. Where VTHA represents the under symmetric case and VTHS represents the under asymmetric and the symmetric case respectively. See, next we did what? First we did the here we have to validate the simulator with the your model data. Here line represents what? Your analytical modeling. Dimensions that we have considered. As you can see in the SMG device, it shows the more horizontal electric field compared to the your DMG device, and the better matching is obtained between the simulation and the analytical modeling in the DMG FinFET in terms of electric field. Okay, so these are the various dimensions that we have considered. Similarly, as you can see, the surface potential. This is the surface potential for two different value of drain bias. The drain bias we have considered 0.5 and 0.8 volt. As you can see that there is no that much of change of minimum potential as we increase the drain bias. Okay, and the better matching is obtained between the simulation and the analytical data in terms of surface potential. Similarly, the minimum potential also for various gate we have observed minimum potential versus gate length as a function of what? Fin thickness. And as you can observe from this figure 37b, a better agreement is obtained between the simulator and the what? Simulator and the analytical modeling in terms of your minimum potential also. Next, we have plotted the your surface subthreshold swing. See, for this purpose, we have taken the your minimum leakage path concept. We have considered minimum source barrier under your source channel junction. We have considered, and we have observed that the better matching is obtained in case of with respect to channel length as well as with respect to difference in the work function. Del W represents the difference in the work function between metal 1 and the metal 2. In that case, we have fixed the metal 1 work function value. Only we are bringing the metal 2 work function value we have fixed. Only we are changing the metal 1 work function value. And we have considered these are the various minimum leakage path that we have considered. Okay, and we have observed that for leakage path of 0.2 at 0.25 height of the, we got the better matching between analytical modeling and the simulation in terms of your in terms of your what? Yeah, subthreshold swing. Okay, in both the case. Similarly, we have plotted the threshold voltage also by using the minimum barrier path, minimum leakage path. Okay, and better matching is obtained for both your with respect to difference in the work function value and the channel length value in case of your between analytical modeling and the simulation result. Okay, so up to this, whatever we discussed, that is what? That is your analytical modeling in the DMG FinFET. Okay, so next final topic of today's discussion is the application of step device as inverter. So without the applications, the works will be incomplete. That's what we have. We have designed an inverter structure using the ticket simulator. In the ticket simulator, we have designed this P FinFET as well as the N FinFET. Okay, and we have observed the VTC characteristics, transfer characteristics, and we have also did the comparative study between conventional FinFET, step FinFET, and also one case we have considered the channel material will be your gallium arsenide based channel. Okay, and this is the corresponding transfer characteristics, voltage transfer characteristics of the complementary FinFET. So as you can see in terms of delay, this is the table. The average delay is more for conventional FinFET, and it is lowest for your step FinFET. As step FinFET has what? Your better electrostatic control. That's what it has. Due to having the less gate capacitors, it has less delay. But the gallium arsenide, it has more average delay compared to conventional FinFET also, because the gallium arsenide, what happened? The gallium arsenide has what? It has high value of dielectric constant, as we know. Due to having the high value of dielectric constant, the capacitance is also more. That's why the delay also more in case of gallium arsenide based FinFET compared to the step as well as the conventional FinFET. Similarly, we have considered your source. We have considered the source in this case heterojunction your FinFET structure to perform the inverter to examine the inverter performance. We have considered the SiG as the source material in both P FinFET as well as the N FinFET, and we have done the comparative analysis. Okay, as you can see, we are varying the work function value of the, sorry, not the work function, mole fraction of the your SiG material. We have considered three different mole fraction, 0.2, 0.4 and 0.6. And this is the figure what figure 41 represents the your what drain current, that means the linear scale. As you can see, the linear current as the mole fraction increases, the on current of the device increases, increasing in the capacitance value, and due to having the more gate control. But the energy band gap also reduces as what happened. As you can see, the energy band gap also reduces specifically in the conduction between this source region and in this conduction region. As you can see, in this source region, the energy band gap reduces as the mole fraction increases, because as the mole fraction increases, your energy band gap reduces. It is already established, formalized there. Okay. Similar gate capacitance, because as the mole fraction increases, the dielectric constant of the channel material, that means the dielectric constant of the channel material increases. That's what your gate capacitance also increases as the mole fraction value increases. And this is the your corresponding BTC curve, and this is the corresponding your transient characteristics of the for various mole fractions value. Okay, so this is the from that transient characteristics and the voltage transfer characteristics, we have calculated this noise margin and the average delay. Okay, as you can see, the high state noise margin is increases as the mole fraction increases, whereas the low state noise margin reduces as the mole fraction increases. Okay, that means it provides the better performance as the mole fraction increases of the source side of the SiG source FinFET. In terms of delay, as expected, as capacitance increases, the delay also increases as the mole fraction of the SiG source material, that means heterojunction FinFET means in terms of delay, it provides the degraded performance as the mole fraction of the SiG source increases. Okay, then the next will conclude this will summarize this work. What we observed, the step FinFET satisfy the ITRS requirement of the on current in the order of 10^10. Similarly, also we observed that the variation in the threshold voltage reduces as we increase either the channel length or the FinEET, as we have observed, because the reduction in the because the increase in the number of within the gate area. Similarly, the on current and the off current also provides better performance as the dimension increases. The significantly increases insignificant to dielectric constant, whereas the fluctuation in the sigma SS is very significant with dielectric constant. And the distribution, as you observe, the distribution plot for various electrical parameters is close to normal for small grain size and becomes bimodal at larger grain size. Also reported what the germanium-based step FinFET, and also we have made the comparative study in terms of work function variability of the electrical parameter. And it is seen that the germanium device shows the lesser sigma VT than silicon step FinFET. And the dual and the triple material gate FinFET has better RF and the analog characteristics than the single material gate FinFET, as you have observed. And the complementary, that means the CMOS based step FinFET has lesser intrinsic delay than the conventional as well as the telemetry. And also we have reported the analytical modeling of the DMG FinFET. We observed that the analytical modeling thus shows good accuracy with the ticket simulated result in terms of your surface potential, minimum potential, also your subthreshold swing, and the another thing is your threshold. Then see, these are the whatever I did, I have presented, but you also carry out some work or carry out some research, statistical simulation. You can do some your non-conventional geometry also, like eye gate FinFET, or even in the tunnel FET also. Tunnel FET already people have started working in the tunnel FET. You can do the tunnel FET, the work function variability, or similarly, another structure is their vertical super thin body, VSTB FET board, VSTB FET. In that one also you can perform the statistical simulation due to variation in the work function of the metal bit. Okay. So whatever we have reported, only the simulation. Whenever we have done the statistical part, we have only reported the what simulation work. So the analytical estimation variation in the work function is also one of the major research work that you can pursue. The analytical estimation of the variation in the electrical due to presence of work function variation of the metal gate. Similarly, whatever the step FinFET we have implemented on your inverter. Similarly, we can implement circuit or any RAM circuit by using this step FinFET structure. See, whatever we have done the simulation, in the simulation not consider the trap effect. The trap effect in the FinFET architecture we have considered. Okay. Similarly, while doing the modeling, also you have to consider the fixed structures and those things. Okay. That means you can. This can also be one promising work that you can carry out research. Then effect of work function variability in the ferroelectric FinFET. Nowadays, people are doing the work on the ferro devices also. That is also one of the major research scope that you can do to find out the means the work function due to metal gate. You can you can consider the ferro devices also. Okay. Similarly, another point is what the another research area is the impact of lateral struggle in FinFET structure. See, what lateral struggle means what? When you do the deviation in the source and the drain, then due to some tilt angle, due to some means diffusion process, the source and the drain, what will happen? It will extend to the channel, and which leads to the reduction in the channel length. And due to the reduction in the channel length, it has severe impact on the electrical parameters, and will lead to the what? Variation in your electrical parameters. That means, see, this type of analysis, the impact of lateral struggle is is there in the FinFET structure, but FinFET structure is not yet reported. You can carry out some research in the FinFET structure also. Okay. See, these are the few research scope that we have. Okay. These are the few references that I have taken for this presentation. Okay. Thank you and stay safe. I think few queries are there.
Rajesh sir, students are asking for permission of Google Form solution.
Huh?
Test link I have posted in the chat box. They are asking for permission. कुछ ऐसा है तो इधर आपको देखो मेरे पे करो. Test is asking for permission.
But no message comes.
मुझे दिख रहा है वो प्राइवेटली सेंड कर रहा हूँ.
So few questions are there.
दो क्वेश्चन है. 2 क्वेश्चन कर दिए, आप पढ़ सकते हैं? हेलो?
Yes, sir. But no permission for that Google form.
हाँ, it was work. नहीं, वो लिमिट टू MNIT तो नहीं करती आपने गूगल फॉर्म में, वो क्रिएट तो करना पड़ेगा,
अच्छा अच्छा, one.
है ना?
Yes,
लिमिट
yes.
टू MNIT को हटा दीजिए।